Assalamualaikum and selamat sejahtera. I am Afiq from Group 3. Our group will present about major losses in pipe experiment. This is our group members, which is Muhammad Afiq bin Muhammad Sabri, Syirawan anak lelaki Pranet, Muhammad Ifan bin Ramizu, Muhammad Haikal bin Badaru, Nur Hazwani binti Muhammad Sobri. Our lecturer name is Dr. Wan Rosli bin Wan Sulaiman. Okay, first of all, I will present about introduction for this experiment. In this experiment, the pressure loss or the head loss for a flow subject to friction will be determined experimentally. The flow is considered steady at Reynolds numbers where Re greater than 2320. Factors needed in calculating total head loss are velocity of the fluid, length of the pipe, the roughness of the inner wall of the pipe, and the last diameter of the pipe. Uh, the objective we use the main objective for this experiment is to determine pipe friction factors or resistance coefficients. The apparatus we use for the experiment are rotameter, thermometer, gate valve, various measuring sections, digital display for pressure, pump switch, main switch, electronic pressure sensor, return hose, pump, drain valve, various measuring sections, water tank, interchangeable measuring objects, differential pressure sensor, 6 tube manometer, 2 tube manometer, and the last one is return valve.
Hi, I am Azwani and I will present about the theory for this experiment. Alright, so for the theoretical part for this experiment, generally in turbulent pipe flow between 2 points of horizontal pipe, the pressure loss and major head loss could be determined by using Bernoulli equation. So here we have two formulas. The first one is the pressure loss formula, which is P is equal to the friction coefficient over inner diameter times 2 times with the density of flowing medium times with the velocity of flowing medium. And the second formula, we have the major head loss formula, which is HL is equal to the friction coefficient over inner diameter times with the velocity of flowing medium over 2 times with the gravity constant. Next, for turbulent pipe flow, friction coefficient depends on first, equivalent pipe roughness, and second, Reynolds number. So we can obtain the equivalent roughness of the pipe by referring to the table here. As we can see, different pipe will provide the different equivalent roughness. We can also obtain the friction coefficient by using the Moody's chart. As we know, Moody's chart shows the relationship between the Reynolds number, the friction coefficient, the equivalent pipe roughness, and also the inner diameter of pipe. And here is the table of kinematic viscosity of water as a function of temperature. So the kinematic viscosity is required in order to calculate the Reynolds number. So Reynolds number formula is shown here, which is Reynolds number is equal to the average velocity of fluid times with the inner diameter over the kinematic viscosity. And on the other hand, we can also calculate the speed of flowing medium by using this formula. And as we can see here, there are other three formulas that can be used to calculate the friction coefficient. First one is Blasius formula, which is used for hydraulically smooth pipe. And next, we have Coolbrooke formula, which is for pipes in the transition. And lastly, we have Moody formula. That's all from me. Thank you.
Hi, Assalamualaikum. My name is Muhammad Haikal bin Hisham. So for my part is I will explain to you about metallurgy part. So basically, methodology part divided into two parts. There is apparatus and procedure. So let me explain to you about the apparatus that used in this experiment. So in this experiment, to complete it, we use 19 apparatus, all of it. The first one, as you can see that is rotometer, the yellow one. The second one is two tube manometer, the black one. Number three is six tube manometer. Number four is differential pressure sensor. Number five is digital display for pressure, the square one. Number six is pump switch that is covered behind the box. Number seven is main switch, also covered at the side of the box. Number seven, electrical pressure sensor, this one. Number nine, return hose at the end of the pipe, this part. Number 10, return valve here. Number 11, interchamber measuring object. Number 12, water tank here, the square one. Number 11, drain valve, overflow. Number 12, the pump. Number 13, various measuring section. Number 14, feeding hose. Number 15, number 16, gate valve. Number 17, number 18, thermometer. And the last one, the variable type is we are dividing into three variables for this experiment. The type of pipe, that the first one is steel, the copper, and the PVC. Okay. The next one, we are going to the procedure. So, in our first procedure, how to complete this experiment, first step is both feeding and return hose are connected to test pipe section. Here is the feeding pipe and the right one is the return hose. Number two, the second step is the manometer tube. At one of the two tube manometer has one valve here, the left one, and H2 outlet here, the right one, are connected to test the pipe section. The third procedure, the third step is main switch and pump are turned on. The main switch is the red one, and the pump switch are the green one. The fourth step is the gate valve are opened slowly until the reading of rotometer or actual flow rate reach 2 meter cube per hour. Here, the valve, the gate valve. Okay, the fifth step is the ventilation valve, the black one. On top of the tube, two tube manometer is open by turning it anti-clockwise direction to let the water overflow from the system. Here, the tube overflow. The sixth step is the gate valve is closed and the pump is turned off. The gate valve is closed and the pump will turn off. The seventh step is the ventilation valve, the white one, of two tube manometer is open until the preset minimum reading of two tube manometer reach. For example, of this image, we are using 25 mm for galvanized steel pipe, 25 mm FPR PVC pipe, 1 mm for rotor copper pipe, 1 mm for PVC 20 pipe, 1 mm for PVC 32 pipe. Next, the X. The gate valve is opened slowly until the level of water at two tube manometer of H1 reach the maximum while H2 at the minimum. H1 is the left one, H2 is the right one. Okay, the ninth step is the two tube manometer reading H1 here, H1 and H2 temperature and Q at voltmeter is recorded until when we are getting the reading. The 10th step is the QX is reduced to 5 different value by adjusting or reducing the opening of the gate valve. Here, the opening gate valve. The 11th step is the manometer tube at the two tube manometer is transferred to the differential pressure sensor. Here, manometer tube will be transferred to the differential pressure sensor. The 12th part is the flow meter valve is adjusted based on previous reading. The reading differential pressure is recorded. Here, the reading will be shown. The 13th step is QX is reduced to 5 different value as data before. The reading of the differential sensor is recorded again. The 14th is the gate valve is closed and the pump is turned off. The feeding and return hose changed to another part section. The 5th step is we are going to repeat our step from step 2 to step 14 for another pipe. That is 3 pipes that we are used for this experiment. So I think that's all for the procedure. Thank you very much.
Now we move to the result. Table 3 shows the data of the galvanized steel pipe. It has internal diameter 12.7 mm and the length of the pipe is 1000 mm. The average flow meter is 0.4. Next is table 4, which is a data for a copper pipe. It has outer diameter 80 mm, thickness 1 mm and the length of the pipe is 1000 mm. The average flow rate is 0.9. Next, table 5 shows the data for the PVC pipe. It has outer diameter 20 mm, thickness 1.5 mm and the length of the pipe is 1000 mm. The average flow rate is 0.45. Next is data for PVC pipe. It has outer diameter 16 mm, thickness 1.8 mm and the length of the pipe is 1000 mm. The average flow rate is 1.0. And the last one is table 7. The table 7 is the data for PVC pipe. It has outer diameter 32 mm, thickness 1.9 mm and the length of the pipe is 1000 mm. The average flow rate is 1.7. Next, we move to the discussion. The first topic to discuss is compare the coefficient of the friction for each of the tested pipe in your experiment with the coefficient of friction from Moody chart and the calculation using the formula of Bessel, Colebrook and Moody. Explain on the possible reason for the difference in their value. The first calculation is for galvanized steel pipe, where we need to find the velocity by using the equation V equals to 4 Q average over 5 times diameter square. Next, after we have the value of the velocity, we put in the formula of the Reynolds number and we get 30,909.32. Next, after that we can find the value of F, which is coefficient friction, from the Moody chart, and we will get 0.041. From the Coburg formula, we also get 0.041. From the Blasius formula, we get 0.029, and from the Moody formula, we get 0.058. Next is a question for copper pipe. We will get velocity equal to 1.243 and the Reynolds number equal to 25,751.65. After that, we can obtain the value of F from Moody chart, and we will get 0.025. The value of F from Coburg formula is 0.0252, and the value of F from Blasius formula is also same, but the value of F from Moody formula is 0.047. Next is the calculation for PVC pipes 20 mm times 1.5 mm. We will get velocity equals to 0.5507, and the Reynolds number is 12350.30. The value of F from Moody chart is 0.029. The value of F from Coburg formula is same, and the value of F from Blasius is also same. The value of F from Moody formula is 0.006. Next is the calculation for PVC pipes 16 mm times 1.8 mm. We will get velocity equal to 2.3 and the Reynolds number equal to 38718.44. After that, we can get the value of F from Moody chart, which is 0.023, and the value is same for Coburg formula and Blasius formula, but the value of F from Moody formula is a bit different, which is 0.0041. Next is the calculation for PVC pipes 32 mm times 1.9 mm. The value of velocity is 0.756 and the value of Reynolds number is 29224.4. After that, we can get the value of F from Moody chart, which is 0.027, and the value from Coburg formula and Blasius formula is also same with the value of Moody chart. The value of F from Moody formula is a bit different, which is 0.0045. The possible reason for the differences in the coefficient of friction value for Moody chart and calculation using formula of Blasius, Coburg and Moody formula. There are few things that we need to consider when calculating friction coefficient. The result of the calculation depends on the type of the flow, such as turbulent flow, laminar flow, and transition between turbulent and laminar flow. The value of friction coefficient obtained from the Moody chart for all pipes except for the galvanized steel pipe are the same when calculating using the Blasius formula and Coburg formula. However, there are slightly different values when compared using the Moody's formula. The reason is because the Moody formula stated that the accuracy of the smooth pipe are about approximate 5% and approximately 10% rough pipe. The value of the friction coefficient obtained from the Moody chart for galvanized steel pipe are same with the value obtained from the Coburg formula. However, the value show a huge difference when compared to the value obtained from Blasius formula and Moody formula. This is because the calculation of Blasius formula are not as detailed as Coburg formula. As for the Moody formula, the difference is because the accuracy of the smooth pipe are about 5% and 5% for smooth pipes and 10% for rough pipes.
Hi, I'm Irfan. Let's continue the discussion. The question 2 is rank the pipe in ascending trend based on their major head loss value obtained from your experiment. Briefly explain on the factor that influence your pipe ranking selection. First of all, we use the head loss formula, which is FL over D times V squared over 2G. HL is major head loss, F is coefficient of pipe friction, L is length of the pipe, D is internal diameter pipe, V squared is square of the speed of flowing medium, G is gravity constant, which is 9.81. First, we calculate the head loss of galvanized steel pipe and we get head 0.1266 meter, followed by copper pipe. The head loss is 0.123 meter. PVC pipe with 20 times 1.5 millimeter. The head loss is 0.02251 meter. For the PVC pipe with 16 times 1.8 millimeter, the head loss is 0.4169 meter, and the last is PVC pipe with 32 times 1.9 millimeter. The head loss is 0.0248 meter. From the result, we can conclude that PVC pipe with 20 times 1.5 millimeter is the lowest head loss, followed by PVC pipe 32 times 1.9 millimeter, copper pipe, galvanized steel pipe, and the highest is PVC pipe with 16 times 1.8 millimeter. Based on the experiment, we can conclude the PVC pipe with 16 millimeter times 1.8 millimeter have the biggest head loss compared to others pipe. This is because due to the fact that has relatively higher velocity and friction factor as well as small internal diameter. The third question is factors contributing to errors and inquiry in experimental data and the possible recommendation to improve the existing results. The first error is parallax error, and the recommendation is observer's eye must perpendicular to the scale. The second is presence of air bubble. Make sure no air bubbles in the tube before starts experiment. And the last is connection of rubber tube and valve. Make sure the rubber tube is connected tightly. For the conclusion, this experiment is conduct fulfill the objective which is to determine the pipe friction factors and resistance of coefficient. Major losses is one of the energy losses that happen inside fluid transportation pipe. This losses is due to the friction along the pipes. By completing this experiment, friction factors and resistance of coefficient is calculated. Coefficient of the pipe friction also determined by Moody chart, Moody formula, Blasius formula, and last Colebrook formula. The main difficulty that arises when to determine the major head loss is due to the many calculations in order to obtain the results. To sum up, head loss is directly proportional to friction factor and velocity, while inversely proportional to the diameter.
It's gonna be